Friday, though we still meet twice this week. We meet Tuesday and Thursday. But we look forward to a day off on Friday. Next week, we still meet Tuesday and Thursday, but Wednesday, if you haven't heard yet, is advising day. You guys plan on seeing your advisor that day to talk about your interim and spring schedule if you haven't done so by that point. In our class today, in Lecture A, we'll continue with binomial and Poisson random variables. Talk about spreadsheet usage. We're not going to quite get to simulation yet today, but we are going to get back to using a spreadsheet, and you're going to have an electronic assignment due next time. Something called a normal approximation to binomial random variables. Sometimes those binomial coefficients can get really, really big, and so it gets hard to work with. And a normal approximation actually ends up being easier in those situations. Lecture B will probably, Lecture A will spill over a little bit into Lecture B, but otherwise we're going to be talking about, at the start of Chapter 6, confidence intervals to estimate a population mean when the population standard deviation is known. Instead of just one number, x bar, to estimate a population mean, we're going to expand that point estimate to an interval estimate to give ourselves a cushion. All right, which will be a common thing to do in statistics. Today's quiz will still involve mostly focus on formulas, and you'll still have some card probabilities to think about, so this will show up on today's quiz again. The next quiz probably will focus a bit more on concepts from Chapter 5. For example, what is a binomial setting? What is a Poisson setting? How do you decide? Can you identify a random variable as binomial or Poisson? That would be a more conceptual kind of question. That probably will show up in the quiz next time. I do have the formula for Bayes' rule up still on the slides here. I'm not going to spend any more time with this today. It was a harder subject, a harder problem-solving kind of thing. You did have it for today's assignment. There still could be a Bayes type of problem on the test, the second exam. So it's definitely something to maybe practice once in a while, right? Thinking about our advice about studying, reviewing things once in a while, trying to remember things, if you can, from scratch once in a while. We used a tree diagram to help us solve the Bayes' theorem problem. Here was the structure of the tree diagram. I don't want to take the time to talk about this, but it would be worthwhile for you to think about it on your own, perhaps, as you work through another Bayes' theorem problem in a week or two. Okay? It would be good to review that at some point. All right, so we need to focus on binomial distributions. Again, our main example that we considered so far was Rod Carews batting from the Minnesota Twins season of 1977. Anyway, I'm not going to look at this information again. What we're going to move forward to is the formula for the binomial coefficients. First of all, when you see this kind of symbolism, first of all, realize this is not a fraction right here, okay? Didn't really mention that. This is not a fraction. This is not n divided by k. It's a symbol for the binomial coefficient. You put the n up there, you put the k down there, and you put them in parentheses. It's just a symbol for one number. The number found by this formula here, n factorial divided by the product of k factorial and n minus k factorial, also denoted nck and described as n choose k. Those are the symbols and the words that we use to describe this quantity. It does represent, in terms of the idea of combinations, which you should have heard about in the past, the number of combinations of k objects taken from a group of n objects. For example, if you have 5 objects, A, B, C, D, and E, and you're wondering how many groups of 3 objects can I take from that group of 5 objects, well, the answer evidently is 10. We're not worried about the order of these objects. Well, we're just after the total number of them, though I will list them in different orders. Well, okay, for any given choice of 3 of these things, A, B, and C, I will not list those 3 things in different orders. That's just one group. That's one group of 3 objects from this group of 5 objects. You could have A, B, C, you could have A, B, D, you could have A, B, E. You could have A, C, D, A, C, E, and A, D, E. Those are the 6 things that have an A in them. 6 groups of 3 that have an A in them. There are evidently going to be 4 without an A. B, C, D, B, C, E, B, D, E, and then C, D, E. Those are the 10 groups of 3 objects that you can take from this bigger group of 5 objects. And this formula claims to give you the right answer for the total number of combinations of 3 objects from a group of 5. We got 10 there too, just like we have 10 things listed there. I don't want to think about reordering them. It's not a permutation problem. Why is this related to binomial distributions? Well, if you think about Rod Carew having 5 at-bats and having 3 successes, 3 hits and 5 at-bats, going 3 for 5. Essentially, the reason there are 10 ways that can happen is because you can pick out of these 5 slots, if you will, representing 5 at-bats, you can pick 3 of them to have the success. They could be the first 3. You could go S, S, F, F. S, 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 F, F. Or it could be the first 2 and the 4th one having the S's, and the other 2 having the F's. It could be the first 2 and the last one having the S's, and the other 2 having the F's, etc. Each choice of 3 slots, 3 at-bats that are going to get the hits, that are going to be successes, corresponds to one possibility, one choice of a group of 3 objects from this group of 5 objects, a group of 3 slots, or 3 at-bats from a group of 5 slots or 5 at-bats. That's, in essence, why this formula gives the right answer as far as the number of ways, in this case, 3 successes and 5 at-bats can happen. These coefficients do show up in Pascal's triangle, and you should know that. You should know how Pascal's triangle is constructed. You put 1s along these diagonals, and inside, for any given position, like here, that number is the sum of the 2 numbers most directly above it. 3 is 1 plus 2. 10 is 6 plus 4. 20 is 10 plus 10, etc. The next row, for example, would be 1, 7, 21, 35, 35, 21, 7, 1. These numbers in Pascal's triangle, if you create this triangle with this pattern, are binomial coefficients. For example, this 10 right there is the same as 5 choose 3. That's the example that we did. This 21 is the same as something that's not shown on here. It would be what? Let's see, I think it's 7 choose 5 should be 21. We can check it with the factorials. 7 factorial divided by 5 factorial times 7 minus 5 factorial. That's the formula for that binomial coefficient. 7 factorial is the same as 7 times 6 times 5 factorial, so I can cancel the 5 factorial on the bottom like this. Then I'm left with 42, 7 times 6 over 2, which is 21. That matches the circled number there. Okay? So you should take the time to think about that and work through this and check it through the line. These numbers do come from Pascal's triangle. They match the numbers in Pascal's triangle. Why are they called binomial coefficients? It's related to something called the binomial theorem. A binomial in math generally represents a sum of 2 things. Binomial, it's got 2 things in it. And the binomial theorem tells you how to expand binomials, powers of binomials. For example, if you want to expand x plus y squared, you should remember from FOIL that you would get first times first is x squared, outside times outside is xy, inside times inside is yx, last times last is y squared. But x times y and y times x are the same thing by the commutative property for multiplication. So you can combine those like terms to get x squared plus 2xy plus y squared. Those numbers, the coefficients 1, 2, and 1, are the 3rd row of Pascal's triangle. And they are binomial coefficients that you can get by doing, in this case, 2 choose 0, 2 choose 1, and 2 choose 2. And it works for the other ones too. X plus y to the fifth, for example, equals this. And those numbers, those coefficients, 1, 5, 10, 10, 5, and 1, come from Pascal's triangle. They are binomial coefficients. That's why it's called the binomial distribution. Okay, and you should know that. They can be sort of fun. You should be able to do these kind of computations. We did an example last time. Maybe we should do one more quick example. You do need calculator help typically to get the final answer still. So if I gave you one like this on the quiz without a calculator, it would have to be fairly small numbers. I think we did 20 choose 9 last time. Let's try about 30 choose 14. This is 30 factorial divided by 14 factorial times 30 minus 14 factorial. It's worth taking the time to write this out to a certain degree. 30 times 29 times 28 times 27, bear with me here, times 26 times 25 times 24 times 23 times 22. I did pick a long one here. 20 times 19 times 18, almost done, times 17 times 16 factorial. I can stop there because I'm going to want to divide out the 16 factorials. I am going to write out the 14 factorials. 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. The 16 factorials will cancel. And it turns out everything on the bottom will completely cancel out as well. Got to be a little careful with this. 14 there will cancel with the 28, for example, to leave a 2. 13 will cancel with the 26 to leave a 2. 12 can cancel with the 24 to leave a 2. Keep getting 1s on the bottom. 11 can cancel with the 22 to leave a 2. 10 can cancel with the 20 or the 30, it doesn't matter. I guess I'll cancel with the 20 to leave a 2 there. 9 can cancel with, for example, the 18 or the 27. Maybe I'll continue the pattern, leave a 2 there. 8. Now I made it a little trickier on myself. I could cancel this 8 with 3 of the 2, since 2 times 2 times 2 is 8. Cancel those 3 2s. The 7 can cancel with the 21 to leave a 3. 6 can cancel with the 30 to leave a 5. This 5 can cancel with that 5. This 4 can cancel with what's left? A 2 times 2. Let's cancel those 2 2s. This 3 can cancel with this 3. And this 2 can cancel with this 2. So as long as you're careful, I hope I was careful enough, you can do this calculation. Everything on the bottom became a 1, it canceled out completely, so you can ignore the bottom. Focus on the top, focus on the ones that are not 1 in the top. What's left over? Better do it wide enough to see both of these things here. Over here. What's left in the top? I got a 29. Not surprising because that's prime. Got a 27. I didn't cancel the 27 with anything. I could have canceled it with the 9 or the 3. 25. I could have canceled that with 5, but I didn't. 23. 19. 17. Did I miss any? Does that look good? Evidently that's the answer. That's what? 145,422,675. Is that the right answer? We could check it with 30, choose 14. Do a 30. Go to your math menu, go over to PRB. PRB. Go down to NCR. Then do 14. It is the exact same number. Okay? So I think that's kind of fun. I like canceling things. So I hope you don't mind it too much. I probably wouldn't make you do one quite this big on the test. But probably there will be one where you have to do that calculation in the test. At some point, just not quite as big. What are the binomial random variables? What's the binomial setting, really? We applied it to Rod Carew's baseball at-bats, thinking of a finite number of at-bats, 5. That was the number of trials. You got a fixed number of trials called n. You count the number of successes. X represents the number of successes. It counts how many. Could be 0 successes. You could go 0 for 5. Could be 1 success, 2 success, 3 successes, 4 successes, 5 successes. If n is 5, you have to stop there. If we were looking at 10 at-bats, we could go up to 10. So you got a fixed number of trials, n, and you count the number of successes. P is the probability of success on each trial, and you assume the trials are independent of each other. How he does on this current at-bat is independent of what happened on previous at-bats. That's the assumption. It's the assumption that allows you to use the multiplication rule to derive the formula, essentially, in conjunction with the addition rule. And here is the formula for the probability of k successes. So understand this notation. K is a fixed number like 0, 1, 2, 3, 4, etc. To find the probability that x equals k, x is your variable, you do this computation. Let's do another example. For example, if we consider a baseball player who's not so good, maybe p is 0.2, so that 1 minus p is 0.8, and you're wondering what is the probability that that player who's not so good maybe goes 2 for 4. Let's let n be 4. What's the probability that that baseball player gets 2 hits in 4 at-bats? This formula will give it to you. The 2 that I put right there, that's the k. The answer is 4, choose 2, n is 4, k is 2, times p to the k power, 0.2 squared, times 1 minus p, 0.8 to the n minus k power, 4 minus 2 power, which is also second power. 4 choose 2 is 4 factorial divided by 2 factorial times 2 factorial, because 4 times 4 minus 2 is 2. 0.2 squared, I hope you can do that in your head. That's 0.04. 0.8 squared is 0.64. That's 24. This is 4. So you get 6 times 0.04 times 0.64. How much can I do in my head here? 6 times 0.04 is 0.24. Guess I'll do a calculator at this point. About 1/4 of 0.64, so it's going to be close to 0.16. It'll be 0.15 something. 0.24 times 0.64 is 0.1536. That's your probability that a baseball player who is not such a great hitter, a 200 batting average, 0.2 is its probability of success. 1 out of every 5 official at-bats he gets a hit. What's his chance of going 2 for 4, getting 2 hits in 4 at-bats? There's how you do it. Okay? And you could probably expect one where you'll have to use this formula on the test as well. And you should know the formula for the quiz and any future quizzes. Without getting into details, the binomial theorem that talks about expanding binomials allows us to verify that this generates what's called a valid probability model. Well, certainly all these probabilities are not negative, but they also add to 1. You'd have to prove that the sum of those things is 1. I'm not going to do that, okay? If you feel like you're mathematically inclined and would like a challenge, I would encourage you to try proving that. It does involve using that binomial theorem where the coefficients come from Pascal's triangle. Okay? If you feel like you're up for a challenge. You're not required to do that, but maybe you want to try. But the point is, the sum is 1. that makes it a valid probability model. It doesn't mean it's an accurate probability model. It means it's valid. Okay? The probabilities are not negative and they add to 1. That's what makes a valid probability model. Again, what is a binomial setting? I said this verbally a few minutes ago. I will go on to the next slide here. You should know this slide is here, talking about successes and failures, certain number of trials, you're counting the number of successes. Probability of success on each trial is constant, and the outcomes are independent of what happened previously. And again, x counts from 0 to n. Here's how to do it in a spreadsheet. And this is going to be related to your electronic homework for next time. You use a built-in function equals BINOMDIST. That function has 1, 2, 3, 4 inputs, 4 arguments. The first one is k, which is the number of successes you'd like to know the probability for. The second one is n, the number of trials, like 5 for Rod Carew. P is the probability of success, and then cumulative means put either false or true in that last spot. False means you're calculating a singular probability, the probability that x equals k. True means you're calculating this other probability, a cumulative probability, the probability that x is less than or equal to k. And this is a discrete random variable, so putting a less than or equal to there is important. Don't put a less than. With continuous random variables, it didn't matter. But with discrete ones, where you use these formulas to find the probabilities, and you've got, for example, finitely many outcomes, you have to pay attention to inequalities like that. Less than or equal to, not less than, is what this gives. So let's give this a try on the spreadsheet. So we have to, again, have a fixed number of trials, n, a certain probability of success on each trial. Let's do 10 trials this time. And let's consider the baseball player who's not so good. A 0.2 probability of success. The k values are the same as the x values. K I'm thinking of as being specific values. X I'm thinking of as being a variable, but these are the x values. He could have 0 successes. He could go with 0 for 10. 1 success, 2 successes, etc. Here's a quick way to add 1 to those. I can keep adding 1 to the next value of k with a formula like that. K goes up to 10. What's the probability that x equals k? Use that equals BINOMDIST. They tell you the syntax here, number of successes, that's the k. Number of trials, that's the n, which is in cell B1. Probability of success, that's the p in cell B2. Cumulative, we're going to do a false here because it's the probability that x equals k. So, again, k is the first argument. N is the second, which is in B1, and I better use dollar signs to make that cell reference fixed. B1 with dollar signs. P is the next one, B2 with dollar signs. And then false, or 0 stands for false as well. You can use 0 there. I do not want cumulative. I want the probability that x equals k, not the probability that x is less than or equal to k. What's the probability that a 200 hitter will go 0 for 10, 0 for 10? Oh, it's fairly small. About an 11% chance. What's his most likely number of hits, do you think, in 10 at-bats? Which one do you think has the highest probability? 2. He's a 200 hitter. It doesn't mean the probability of getting 2 hits is bigger than 50%, though. I bet it's less than 50%, but it's going to be the highest one. It's about 30%. Okay? You can do a cumulative one as well. What's the probability that x is less than or equal to k? Do the same syntax except put a true at the end instead of false. K, comma, B1 in dollar signs, comma, B2 in dollar signs, put true at the end. For the first one, it's going to be the same answer because the probability that x equals 0 is the same as the probability that x is less than or equal to 0. So this first one is the same. The second one, though, is going to be bigger than 0.26. It's going to be 0.107 plus 0.268 or so. 376, I think, with rounding. Yep, 0.376. Keep adding on. You'd add on about 0.302 to the next one. You get that, etc. These numbers have to eventually come to 1. This last one is a 1. These numbers in column C have to add up to 1. They do. Try it. Add these numbers. They add up to 1 because it's a valid probability model. What's the mean? How would I find the mean of this random variable? We've done this before. It was on the first test. Chapter 4. How do you find the mean of a discrete random variable with finding many outcomes? Little hint, it's a summation of what? Anybody? Anyone? Anyone? Bueller? Anyone? That formula. Multiply the x's and the corresponding p's. The x's in this case I'm labeling with k. Maybe I should label it like this. X times p of the probability that x equals k. That really does still represent this product, the x values, the possible x values times the corresponding p values. It's the same thing, just different notation. So cell B5 times cell C5 here. 0 times 0.107, 0. This next one's going to be 1 times 0.268. This next one's going to be 2 times 0.302, 0.604, etc. I'm going to end up doing all those and then add them. What do you think the answer is going to be? You should be able to predict this. What do you think the mean number of successes for this 200 hitter is going to be? 2. 2 out of 10. This should be, when you add them up, 2. And it is. Thus illustrating that for binomial random variables, you actually don't have to use this formula to figure out the mean. Instead, you can take n times p. The number of trials, 10 in this case, times p, 0.2. 10 times 0.2 is 2. For binomial random variables, there's special formulas for the mean and standard deviation. I won't take the time to verify the standard deviation one because we're getting close to quiz time here. These formulas work only for binomial random variables. This one makes good logical sense. N is the number of trials, 10 at bat say. P is the probability of success, 0.2. The mean is 10 times 0.22. It's called the expected value as well. It doesn't mean it's the most likely value as far as, well, in this case it is the most likely value. It doesn't mean it's a higher than 50% chance to happen. That's what I was trying to say. And 10 times 0.2 is 2. It's the expected value, it's the mean. The words expected value and mean are synonyms. This is the formula for the standard deviation, square root of 10 times 0.2 times 0.8 in this case. That would be square root of 2 times 0.8 is 1.6. Square root of 1.6 is, I don't know, 1.2, 1.3. Somewhere in there is the standard deviation of this random variable. So these formulas work as shortcuts for binomial random variables. Wow, we're not going to get to Poissons before the quiz. I guess that'll be after the quiz. However, we can use this for something called a normal approximation. Okay, real quick example. Let's see how quick I can do this. Your internet company advertises that it ships 90% of its orders within 4 working days. You select a simple random sample of 400 of the orders and find that 340 of the orders were shipped on time. Actually, that's a typo. That should be 352. 352 of the orders were shipped on time, which turns out to be 88% of them. If the company really ships 90% of the orders on time, what's the probability that 352 or fewer are shipped on time? Okay, this is assumed to be a binomial random variable. Your number of trials n is 400. Your probability of success of shipping on time is 90% or 0.9. You're wondering what's the probability of getting 352 or fewer for the number of successes, the number that are shipped on time. I'm not going to take the time to make a graph of this distribution, but suffice it to say it looks like a normal curve, even though it's discrete. The mean is n times p. 400 times 0.9 is 360. The standard deviation is square root of n times p times 1 minus p. Square root of 400 times 0.9 times 0.1. That'll be square root of 36, which, hey, is 6. How did that? I didn't plan for that to turn out so nice. That's 6. Pretend that this is a normal random variable. I'll write an approximately equal to sign because it's not exactly normal. Pretend it's a normal random variable with this mean and this standard deviation and standardize. Convert it to a z. Take 352 minus 360. Divide by the standard deviation 6. Negative 8 divided by 6 is about negative 1.33. And if you look in table A, I always do the wrong one. If you look in table A, for z equals negative 1.33, the area to the left of it is, looks like that's 0.1292. Let's say about 0.13. It's about a 13% probability. What does that tell you? It tells you where is it? I lost it. Here we go. It answers part A here. Your chance of getting 352 out of 400 shipped on time is about 13% when you typically ship in the population 90% on time. So your competitor says, hey, you claim that 90% are shipped on time, but in your sample, only 88% are shipped on time.